Hello everyone, I am Anisha. I am presenting the Perlin noise. So first I will present a brief introduction, then I will dive deeper into how we can generate our own Perlin noise, and finally some visual examples. Uh, the first $1,000,000 question is, why do we care about noise in the first place? Well, to render different kinds of graphics components like clouds, terrains, fire, mountains, etc., we actually need noise. For instance, for mountains, what we can do is, let's say we have a 2D area, and for each of the points inside that 2D shape, we feed these points coordinates into a noise function, and we get a value as output. We can use that value as the height of the mountain for that point. We can also use that value as a color of that point to get a truly visually smooth and beautiful noise. So, Perlin noise is one specific kind of noise which is defined in simple mathematics and geometry. Perlin noise relies on randomly generated gradient vectors chosen arbitrarily for each of the points on a square grid. And it creates beautifully smooth and continuous noise when it is repeated along a grid. Now let's dive deeper into how we can generate our own Perlin noise. So what we have is a square, a 1 times 1 square, and what we want is a colorful noise like the one shown in the right. So we have a square, and the first crucial step for us is to have a randomly generated gradient vector at each of the endpoints A, B, C, and D. It is very important to note that the exact directions of these randomly generated vectors will actually determine the color for each of the points inside the square. Now, since we need to determine the color for each of the points inside, let's first pick an arbitrary point P, X, Y, and now all of the endpoints A, B, C, and D will have some contribution on the color of P. First of all, let's take A. So we need to find the contribution of A on the color of P. Now it is defined that this contribution will be proportional to the projection of AP on the randomly generated gradient vector at A. So the gradient vector is A prime. For having the projection, we draw a normal from P, so the normal PQ on A prime, and the projection is EQ. So this length EQ is very important for us. And let's find some mathematical expression for EQ. So we define AP equals R, angle PM equals alpha, and most importantly, angle A prime AP, or the angle at which the gradient vector is in line with respect to the x-axis, is basically theta. Then EQ will be R cos alpha minus theta. Now, if we expand, so R cos alpha cos theta plus R sin alpha sin theta, and it becomes X cos theta plus Y sin theta. And the color 0, actually means the contribution of A on P. So this contribution will actually be proportional to EQ. So how we will actually get this color, that details will be addressed later. And interestingly, there is another way to look at this geometric process. That is, we obtain that EQ equals X cos theta plus Y sin theta. But we can also rewrite it as a dot product between the vectors x, y, and cos theta sin theta. And cos theta sin theta is actually the normalized gradient vector, right? Because this angle A prime AP was actually theta. That means cos theta sin theta will actually be this A prime vector normalized. So, a vector way of looking at the process of generating Perlin noise is the contribution of A on the color of P is basically the dot product between the position vector of P and the normalized gradient vector at A. And it makes very much sense, right? Because very often we take projections or dot products to uh, indicate the effect of something on something else, right? So here the intuition is just like that. And now, how do we get the final value for p? Like we currently what we have is four values for the four endpoints, right? So we need to somehow combine them all to get a final value for the random point p. Uh, to make this process smooth, process generate a smooth image, a fading function is actually used. So this function is like this, a fifth order polynomial, and this polynomial is chosen such that our final color function is differentiable, has a continuous first and second differential or derivative. Okay, so now we will basically do a linear interpolation. First of all, we do interpolation along the x direction, and then we do interpolation along the y direction to get a final value for p. Note that this value will obviously be in the range 0, 1. Now, this value is not actually enough. We need to convert this value to a color value, right? So for grayscale, we can actually multiply this value with 255 to get a grayscale value for that point. And when we do this for each of the points, we will get a grayscale noise. Now, what if we want an RGB noise like the one shown at first? Well, for that, we actually need to use this same function, but for red, green, and blue components separately. So here a way is shown, but it can also be done in other ways. So the idea is this, that we will use the same function but with different offsets or shifts, so that we get different values for our red, green, and blue components. And so far so good. We have so far been confined in only a 1 times 1 square box. Now to get a larger noise, we will need to repeat this process along a longer grid, like n times n grid. Now let's see some visual examples. This is the Perlin noise we obtain when we do the process described earlier on a 1 by 1 grid. And why should we be confining a 1 by 1 grid? Let's expand it to a longer grid, right? So if we try to expand it on a 10 by 10 grid, so and we have the randomly generated gradient vectors for each of the points in this 10 by 10 grid, and finally what we have is a smooth and visually attractive noise like this. So that was all about Perlin noise. Thank you so much.
Hello everyone, this is Kaushik Shah. We've already discussed about Perlin noise, but Perlin noise isn't perfect. It has some shortcomings. Firstly, direction artifacts. Since the algorithm is based on a hypercubic grid structure, it inherently produces stronger correlations along 45-degree and 90-degree angles. Second, computational complexity and higher dimensions. For n dimensions, 2 to the power n number of vertices has to be considered for each cell. As the number of dimensions increases, the computational cost of Perlin noise increases exponentially. Third, the lack of rotational invariance. As you can see in this picture, after rotating by 60 degree, the noise pattern has changed from the original noise pattern. Why does it happen? Because after rotation, although the coordinates of the pixels change, the underlying grid and the gradients of the vertices of each cell stay the same. Thus, the noise values for the rotated coordinates are calculated using gradients different from those used with the original version. Now, can we do better than the Perlin noise? Turns out we can. Introducing Simplex noise. Simplex noise is an improved noise function developed by Kim Perlin himself. It implements a grid structure using simplexes that are the simplest possible geometric shape in any given dimension. Let's see the implementation of simplex noise. In the first step, the input coordinates have to be transformed from a standard orthogonal coordinate system like Cartesian system into a skewed coordinate system that aligns with the simplex grid. We use this formula for the transformation. P is our original point and P prime is the transform point. Now, The vertices of the simplex that contains the point P prime needs to be calculated. Our point lies in this cube cell, and P0 is the base corner. We can find P0 by simply taking the floor of our coordinates. The main diagonal divides this grid into two simplexes. The main diagonal is represented by x equals to y. If x is greater than y, the point is in this region, otherwise the point is in this region. We have already handled the integer part. Now we can consider the fractional part. If x prime minus I is greater than y prime minus j, the point is in this region, and otherwise the point is in this region. And this is how we can calculate the other coordinates of the other vertices. We use these vertices in the next step. In this step, we find the gradient and distance vectors. To find the gradient vectors for each vertex, we simply pass the coordinates of the vertex into a hash function. So the gradients here can be generated deterministically. This is why the gradients are called pseudo-random here. Now we need to unskew the coordinates of the vertices. We use this formula for unskewing. Now we find the distance vector. X and y are the coordinates from our original input point, and xv, yv are the unskewed coordinate points of the vertices of the simplex our point is in. And this is how we calculate the distance vector. Now we need to sum the noise contribution from each of the vertex. This is the formula for our contribution. R square is the radius of the kernel. This is typically set to 0.5 for 2D and 0.6 for 3D. D square is the square distance from our input point to the vertex. If R square is greater than equals to D square, the point is inside the kernel. Otherwise, the point is outside the kernel, and using this method, in that case, the contribution becomes 0. And gradient and distance vector, we have found them in the previous step. How does simplex noise overcome the shortcomings of Perlin noise? Reducing directional artifacts and improving rotational invariance. The grid made of equilateral triangles or simplexes is more symmetrical and does not have strong directional bias of squares. This effectively reduces the directional bias and improves rotational invariance greatly. Second, lowering computational complexity. An n-dimensional simplex has only n plus 1 vertices, whereas an hypercube has 2 to the power n. So, for each cell in a symmetrical cube, only n plus 1 vertices have to be considered. This reduces the computational complexity in higher dimensions by a huge margin. Thank you.
Hello, I'm Jaber, and now I'll talk about fractal noise. Fractal noise is basically multiple layers of Perlin noise stacked together with different frequency and amplitude. This way, we can create more natural looking noise patterns. To generate a fractal noise, first we start with a base Perlin noise. Then we generate several scaled copies of it. Then we adjust the amplitude and frequency for each octave. And finally, we sum them up together to get our final fractal noise. While generating fractal noise, we can have control over multiple parameters. For example, number of octaves, persistence, lacunarity, and seed. Here we'll see how fractal noise varies if we change the number of octaves. Here we can see with low octaves, the noise is very smooth, and as we increase the octaves, the noise becomes more detailed and rich. Now, for the persistence parameter, we can see persistence control the amplitude fall-offs between octaves. So with higher persistence, we can see finer and detailed noise patterns. With low persistence, we can see the noise patterns are very smooth and the details are very faint. So if we increase the persistence, the amplitude fall-offs become faster and the noise becomes more detailed. Here we can see lacunarity variation. So lacunarity is the multiplier for frequency. So if we increase the lacunarity, we will get a rapid increase in the detail of the noise. With low lacunarity, we can see a gradual increase in detail, but with high lacunarity, we can see rapid increase in the detail density. Finally, we have the seed parameter. This is the starting point of the noise generation. Since noise generation happens randomly, so it needs a pseudo-random algorithm for it. So the seed is the initial value for that algorithm. So with different seeds, we can have different patterns. With same seeds, we can reproduce the same patterns. So fractal noise can be regenerated every time if we use the same seed value. So fractal noise can be used in different applications. For example, terrain generation, cloud and water simulation, texture generation for games and movies, data visualization, and art. So in games, we can generate very long terrain with fractal noise, since fractal noise is virtually infinite. So, and if we keep track of the seed, we can generate the same terrain over and over again. Here is an example code for generating fractal noise. So basically, we'll initialize a grid with zeros. Then, for each cell in the grid, we'll generate a noise, which can be Perlin noise. Then we will adjust the persistence, lacunarity, and other parameters for generating the fractal noise. So basically, the persistence will get multiplied with the amplitude every time. So persistence will decrease the amplitude every time it gets multiplied, and the lacunarity will get multiplied with the frequency. So every time it get multiplied with the frequency will change in that ratio. And we are generating, we'll generate these noises for every octaves. So we can have multiple octaves, and finally they will all get summed together, and finally we'll get our fractal noise. So in conclusion, we can say that fractal noise is Perlin noise in multiple octaves, and using fractal noise we can generate natural looking random patterns, and these are widely used in graphics, simulations, and art. Thank you.